Hello and welcome to the Mathematics Institute. It's a lesson on complementary subtraction. Please feel free to visit us at www.mathematicsinstitute.com. We're a small for-profit company. If you like what we do, you can visit us at our website and take a look at what we have here today. So we're talking about complementary subtraction. The first thing to understand about complementary subtraction are what are complement numbers. These numbers in our yellow and orange are complement numbers because they will add together to be a power of 10. What's a power of 10, you ask? Powers of 10 are numbers that look like this. Notice they have 1 as their lead digit and all the other digits in the number are equal to 0. We can actually write our powers of 10 with a base and an exponent. Our base will be, in this case, 10. And our exponent will be equal to the number of zeros that follow our 1. So our exponent here is 3. So we have 3 zeros. We have 4. So we have 4 zeros. Our exponent equals the number of zeros here that we see. So we have 5. It's 5 zeros and 7. Now to solve what complements of a number are, in this case we're going to figure out the complement of 684, we subtract from this power of 10. So we turn these problems into subtraction problems to actually figure out what our complement numbers will be. Take a second here to figure out, first of all, what these powers of 10 are. So pause the video and try to figure out if this is 10 to the 3rd or 10 to the 8th or 10 to the 12th. And then take some time to try to solve each one of these subtraction problems. Time yourself and see how you do. And then at the end of the video, we'll see if you make time getting any faster with your subtracting. So 10 to the 3rd. These are labeled as 10 to the 5th. Next slide. Again, try to solve these first, figuring out what the powers of 10 are first, and then the subtraction solutions. Very good. Let's begin with our examples and how to solve these problems. Now our first box that we have here, we have a power of 10 here, that's our blue number, and our subtrahend is our yellow number here that we're taking away. We'll notice here actually we have a 0 in front of our 273. This 0 doesn't change the value of the problem. We can write the problem like this, but I keep my zeros included for lining up and to show a pattern later on in the rest of the problem, as you'll see soon. So we have our minuend, our subtrahend, and our complement number. Our complement will actually be our answer, which is also called a difference, but this is a special type of difference because we're subtracting from a minuend. Notice that we're the 3rd power here, so we have 3 zeros at the end of our minuend, our power of 10. Now this box here that we just pulled up is actually equal to this box up here. The reason for that is we'll notice that 273 is obviously still equal to 273. And 1,000 is equal to 1 plus 999. We'll notice that actually this front digit on our minuend is reduced by 1, which becomes a 0 here. That's important for later lessons as well. Just note that right now, please. Now we're going to solve actually this operation here of this 999 minus 273 up here first. Because our top number consists of all 9s, there's no need to borrow our subtraction. So our answer becomes easy. Now these two pieces, this green and this yellow and the blue, are equivalent to each other. So we're going to make a substitution. Substituting this blue and yellow piece right here for this green piece. These are equivalent. Which means that all 3 of these sections right here are equivalent to each other. They're all equal to this answer here. And so if we're looking for our initial problem with a pattern, that our last significant digit will add up to 10. 3 plus 7 makes 10. All other digits will add up to 9. 7 plus 2 make 9. 2 plus 7 make 9. We got our 9s from up here. Let's take a look again at this problem. Very similar. Not a whole lot different, so we'll just kind of run through these quickly here. Notice again, these are equivalent to each other, so we're going to perform a substitution, which is the The substitution is noted with these red brackets here, showing that those are still equal to each other. All these are again equal, which will give us our answer. So our pattern is our last significant digit adds up to 10. 9 plus 1 makes 10. Everything else will add up to 9. 0 plus 9 makes 9, and 4 plus 5 makes 9. Now this one is a little bit different, and I've shown this example because of these zeros here in the front, specifically these two right here. This is equal, these are equal to each other, equal expressions, but I've written the number like this here because we have to remember that these digits are going to add up to 9 still. So we'll take a look. Notice this is to the 5th power this time, so we have 5 zeros. Again, go through here. This is very similar to the last one. We have 5 9s this time, though, because our exponent is to the 5th power with 5 zeros. And notice, though, this is why I actually included the 0 0 down here, is because of this subtraction up here. The 0 zeros are kept for alignment and to understand that we're subtracting 0 from 9. That'll give us our answer there. Again, these two are equivalent, so we're going to create a substitution. These are all equal to each other, which is equal to our final answer there. Again, the pattern is that our last significant subtrahend digit adds up to 10. 6 plus 4 makes 10. 0 plus everything else will add up to 9. 0 plus 9 makes 9. 7 plus 2 makes 9. 0 plus 9 makes 9. And 0 plus 9 makes 9. Very good. Let's do some example problems. Oh, excuse me, we have one more left. We'll notice here what's a little bit different is that this last digit is no longer, our last significant digit is no longer in our 1 spot. Don't worry, it won't affect our problem very much, as you'll see. This is the 5th powers from the 5 9s this time. Again, no borrowing from our subtraction. We're subtracting all from 9s. Because those expressions are equivalent, we're going to create a substitution. These 3 pieces are equal to each other, which is equal to this final answer. Again, the same pattern applies, but this time we don't worry about these zeros here in our 1 spot. This is our last significant digit, so 8 plus 2 makes 10, 7 plus 2 makes 9, 0 plus 9 makes 9, and 4 plus 5 makes 9. Alright, now example problems. Take a second here, pause the video, and see what you get for your answers here. These should be instantaneous for you now. I'll start giving you the answers here. Now I've made a mistake on one of these slides. If you can find that mistake, you get a gold star. Not really, but good job. What I'm missing is this 9 right here. I forgot that there should be an implied 0 right there. 0 plus 9 makes 9. I have to include that 9 there. Hopefully you didn't make the same mistake that I did. Do a couple more examples. This one, we'll notice that our last significant digit is now in the 100 spot. Still will not affect our answer very significantly. We'll also notice that we have a 0 here beneath our 0. Because these are equal to each other, we're going to create the substitution. These 3 are now equal to each other, giving us the answer there. Same pattern applies. Our last significant digit adds to 10. 3 plus 7 makes 10. 7 plus 2 makes 9. 0 plus 9 makes 9. Last example, I'll just pull this one up very quickly so you can see how this is done. And then we're going to do one last quiz here. And hopefully, by the end of this lesson, you'll have mastered complementary subtraction. Again, our last significant digit adds up to 10. All our digits add up to 9. Now solve these, please. Pause. Answers. And thank you for watching.